I'd like to thank the faculty for inviting me to speak here today. It's a great honour to talk at this symposium dedicated to Professor Kastler. So, just to introduce myself and my group, we're a group of physicists and engineers who work at the interface of medicine. Our focus is imaging the lungs with hyperpolarised gases. This slide kind of covers the area of technology and engineering and physics that underpin this work, but really the focus and the drive now is to evaluate this technology clinically. Quick overview of my talk. So I'll give you a bit of a background as to the motivation for advanced lung imaging methods. I'll give a brief overview of the work that we've done in the past with helium-3, and then I will focus the rest of the talk on xenon-129 and how we polarize xenon, how we image it, and some of the clinical applications of the inhaled gas in the lungs and in other organs. So if we think about the structure of the lungs, most of the lungs is air. In a healthy lung, maybe 10% of the mass of the lung, the volume of the lung, composes of water molecules. So conventional imaging techniques for imaging the lung, we have computed tomography from X-rays and proton MRI. So water molecule concentration in the lungs is typically low, so conventional proton MRI is inherently weakly sensitive to imaging protons in the lungs. Things are improving though. So when I got into this field about 15 years ago, these were the kind of images we could get with proton MRI in the lungs. Now we can get this kind of image quality, and we start to see some of the structure that we see in computed tomography. So proton MRI is now playing a role clinically, but it's fair to say that both modalities, CT and proton MRI, will not allow us to resolve the small airways, the alveoli. So it's the alveoli where gas exchange takes place, oxygen transfer. We don't have the spatial resolution to resolve these. So these images come from micro-CT, from exosome pathology, and you can see the alveolar structure there, but we don't have the resolution to resolve those structures in vivo in humans. And that's where inhaled gas imaging comes in. With hyperpolarized gases, we can inhale the gas into the lungs. The gas is nuclear sensitive, so helium-3, xenon-129 both have a spin half. We can image them very much like a proton in terms of the MRI methodology. And the distribution of gas in the lungs gives us an immediate picture of lung ventilation. So we see in people with healthy lungs, according to their spirometry, according to the lung function tests, if they've smoked, we see early signs of ventilation abnormality. Patients who've smoked heavily over the years, very much impaired ventilation distribution in the lungs. So this gas is getting right into the physiological workface, the alveolar capillary kind of interface, and can tell us a lot about the physiology. A bit on how we now actually image these gases. How do we get enough signal to image such a low density of spins, given the inherent low sensitivity of NMR in the first place? Well, we use hyperpolarization, and this is where Kastler's innovations have led to the field of optical pumping. Optical pumping of noble gases, helium-3 and 129 xenon, allows this hyperpolarized signal. And then theoretically, we can image these gases in the lungs at any field strength. So going back 16 years, I was a young postdoc, and I got the opportunity to come back to my hometown in Sheffield to work with Edwin van Beek, who's a larger-than-life clinician. Many of you will know him, big personality, ambitious guy. And he'd got together with a consortium of people working with helium-3 in the European Union to put together this FIL project. So it was a Framework 5 project working with physicists in Mainz, here in Paris, clinicians across Europe, and the ambition was to really evaluate helium-3 as an inhaled contrast agent. And I had a great time during that project. To me, it was a prime example of how interdisciplinary research can work and how the European Union can facilitate research like that. So our first images, we shipped gas over from Mainz, so we benefited from the long T1 of helium-3. We flew gas over from Mainz. You can see lurking in the corridor there, that's Jörg Schmiederskamp, who was a student in the Mainz physics department at the time, and a thinner version of myself there. And yeah, we took gas from the cells shipped over from Jörg in Mainz on a weekly basis, and we got images of the lungs. Great project, and it really served as a foundation for us for hyperpolarized gas imaging in Sheffield. So we went on. I spent a lot of time personally and my subsequent students working on refining the imaging techniques for rapidly imaging, volumetric coverage of the lungs. So here we've got dynamic imaging methodology, high resolution volume coverage of the lungs with helium-3. And helium-3 really did serve as a kind of very, very good foundation for understanding what we can learn about lung function and lung physiology with an inhaled gas MRI technique in a variety of diseases. So ourselves and lots of other groups around the world have evaluated this methodology and shown that it can work in a multi-center kind of fashion. And then we were a bit hit by the global 3 helium supply crisis. So you're probably aware helium-3 has applications in lots of other diverse aspects of physics, largely due to the fact that its nuclear spin is very interesting. So probably about 8 to 9 years ago, we were struggling to get hold of helium-3. And so we started looking towards 129 xenon as an alternative gas for inhaled gas MRI. And that was largely driven by availability and cost. So if you look at the costs here for a litre of helium-3 compared to a litre of natural abundant xenon, if you think about this taking off clinically in years to come, xenon is an obvious choice. But the large challenge for us really was back then the image quality was not very good. Helium could be polarized at that time to higher levels, and it's got the inherent advantage that its gyromagnetic ratio is higher, so we get a higher transverse magnetization just by virtue of the fact that the gamma is higher. So really, in order to get better quality xenon images, we need to focus on the technology. Before I review how we go about that, I'll just give you a bit of an overview of what xenon can tell us as a gas. And it's a very interesting atom. Its name's derived from xenos, of the Greek, meaning stranger, and it does in fact have some strange properties, but also very interesting properties from the point of view of NMR. And this is largely due to its large distendable, weakly bound electron cloud. I've mentioned it's gamma, so it's got a lower magnetic moment than helium-3 and proton, which means it resonates at 1.5 Tesla down at 17 megahertz. So that's a relatively low frequency for MRI. As a noble gas, it's diffusive. It's nowhere nearly as diffusive as helium-3, so its Brownian diffusion is more limited in terms of the mean free path in the lungs, but we can still measure its diffusion with MRI. And I've mentioned its cost as well. So if we move on and look at some of the other properties of xenon, again, down to its loosely bound electron cloud, we get a wide range of chemical shifts depending on the environment the xenon is dissolved in. It's soluble in different solvents to lesser and higher degrees. It's very soluble, for instance, in lipids. But it's soluble in tissues as well. So here we can see the xenon in the gas phase in the lungs, so that's xenon in the alveoli. And then we see xenon in the capillaries dissolved in the red blood cell, and xenon dissolved in the tissue and plasma in the lungs as well. And what's interesting is this large range of chemical shift dispersion. And it's due to the fact that this electron cloud has a large influence on the nuclear, the field felt at the nucleus. Interesting properties, though, that we can exploit in a biomedical setting. So, optical pumping of xenon, it would be wrong of me not to mention how we optically pump, given the place I'm in today. So we use spin exchange optical pumping of the rubidium valence electron. So we pump on this D1 transition, which leaves us with a hyperpolarized rubidium atom. And then rubidium atoms collide with xenon nuclei within the optical pumping cell, and eventually we get spin polarization transfer to the nucleus. Now, there's multiple kind of relaxation sinks and spin destruction terms that we have to account for in the optical pumping process when we're looking at rubidium and xenon, and also xenon relaxation terms. I won't go through all of them, but I'll give you a quick kind of overview of some of them, if that's okay. So if we think about the fundamental process of spin exchange, xenon's got an inherent advantage when compared to helium-3, in that the electron cloud of the xenon atom makes its interaction with the rubidium electron more prominent, and we get a stronger contact interaction. So basically we can polarize it faster because of this electron wave function overlap between the electron and the nucleus. And then the challenge then is if we can mitigate these processes of spin destruction and xenon nuclear relaxation, we potentially can get very high xenon polarization levels. Depending on the pressure of xenon in the cell, so at high pressures, it's more of a binary spin flip-flop. At lower pressures, nitrogen buffer gases play a role in van der Waals molecular formation. This cartoon just kind of illustrates how we do things then. So we operate at relatively low pressures, 2 bar, with low xenon concentrations, 3%. And we flow the xenon gas through the oven. First of all, we warm the oven up to give a weak rubidium vapor, and then flow optically pump with circularly polarized light at 795 nanometers, polarize the rubidium electron, and then we flow the xenon through, and we get polarization transfer to the nucleus, and then we extract the gas. So we flow towards the laser, we extract the gas, and then we distill out this 3% fraction. So we freeze out xenon as frozen snow in a magnetic field, and it's got a long T1 in its frozen state, so we can accumulate it pretty rapidly. So fundamental to this process, we're operating here at quite low pressures, 2 bars in this cylindrical cell. What's really helped the field is the availability of narrow line width lasers. So we started out with an external cavity laser, which was self-seeded with a holographic laser, holographic grating, which gave us a nice narrow line width, high power laser. But this was very fiddly, and the open optics didn't really lend itself to a clinical environment. So in recent years, these kind of volume holographic lasers with built-in gratings on the diode have helped massively in making this technology more portable in a kind of clinical setting. So here we've got the integrated optics and the diode with the grating on. And these narrow line widths allow us to optically pump at lower cell pressures, which are beneficial in terms of the xenon polarization process. So in parallel to that, we use long optical pumping cell designs. So this allows us to flow the xenon through very slowly. It allows us to keep the rubidium partial pressure down so we don't get too much spin destruction. And it's kind of a pseudo-static regime, really. And a nice homogeneous high-power laser beam along the length of that cell means that we get very efficient xenon polarization. And it also helps us minimize surface relaxation processes, as we've heard about. So if we look at the kind of efficiency of the process, we're now getting to a situation where approaching more than half of the photons that we actually put into the system induce a nuclear polarization. And that means it's quite an efficient process in terms of deposition of angular momentum into the nucleus of interest. And that's down to optimization of the various parameters in the cell that dictate how efficient the spin polarization transfer is. But essentially, low to medium cell pressures with these long cells help massively. So we're now approaching what we believe to be the theoretical limit of xenon polarization at low flows. So if you think about this, a low flow rate with a large cell with a large diameter and a large laser beam, we can basically get to a pseudo-static limit where we're approaching the theoretical limit of xenon polarization. So that's the motivation for building this big polarizer here in Sheffield, a big long cell there, 5-litre volume cell, Lee Whiting kind of coils for a nice homogeneous field. And this is a 200-watt laser here that we optically pump on the cell. We've only been operating this for last few weeks, really, but we're already getting these kind of performance levels. And this is allowing us to now image basically a patient every 15 minutes. So if we give a patient a dose of half a litre of gas, which is all it's needed to get the kind of image quality I've shown you, we have now got on-demand xenon polarization capability. In parallel, we're looking at some more portable polarizer designs. That's Graham and Guillaume Collier. They've been working on optimizing the engineering side of this. And yeah, a smaller polarizer like this will also work in a clinical setting. That's not to say that there's not other ways of polarizing the gas. You've got the Herzmann polarizer here from New Hampshire, and there's now commercial polarizers out there from Duke. So the original MITI people are now selling polarizers. People are even building them out of 3D printers. So lots of different options, and basically the xenon gas is there to be used. So now I'll focus on what we use it for. So these are the first images that were produced with a hyperpolarized gas by Mitch Albert and the Princeton team back in the late 90s. So that's xenon gas in an excised mouse lung. This is the kind of image quality we're now routinely getting with natural abundance xenon. So that's the cheap xenon. Only a quarter of the xenon in there is 129. But with it being naturally abundant, it means it's much cheaper to produce. It doesn't need enrichment. So that currently markets at about 25 euros a litre, I think. So in a healthcare kind of perspective, it's affordable. I'll just quickly review some of the kind of physics and engineering that we've done in getting to this point. So with this hyperpolarized signal, we can potentially image at any magnetic field strength. So 3T and 1.5T are the two clinical field strengths in the clinic for MRI. And we see that the transverse relaxation times of the signals are pretty long in the lungs at both field strengths. And the resonant frequencies are modest. Normally, proton MRI at 1.5 Tesla, 64 megahertz. The RF resonators are of a different design than one would make for a 17 megahertz resonator. So optimizing the RF coils to pick up the signal from the lungs at these different frequencies is interesting from a scientific point of view. But the interesting thing here is the signal to noise is comparable at the two field strengths. So these images were acquired with spoiled gradient echo, low flip angle images. So we build up the imaging K-space with a small flip angle and then spoil the residual magnetic transverse magnetization before acquiring the next line in K-space. There's a strong argument for recycling the transverse magnetization. The hyperpolarization is finite. Once we've depolarized it, it's gone in the lungs. But we have residual transverse magnetization. Why not recycle it back into the K-space trajectory? And that's what we find with a steady state sequence here. We get much higher signal to noise. So we're routinely using these kind of sequences where we don't spoil the magnetization, we recycle it. And again, at 1.5T and 3T, comparable image quality. Just a quick overview of some of the coil designs we use. So you can do hyperpolarized gas MRI with a coat hanger RF coil. There's nothing clever about it, but if you want to get a nice homogeneous transmit field, a volume resonator like this with a nice homogeneous field, a birdcage resonator is good. Equally good are these kind of vest coil designs, which are close coupled. So the sample and the coil are well coupled, then closer coupling. But you see some inhomogeneity in the transmit field with this kind of coil design. The nice thing about these kind of coils, though, is they can accommodate additional receiver coils inside. So here we have a planar array of 16 receive coils on the front and back. And each of these receive coils has got its own discrete kind of spatial sensitivity pattern. So if we integrate the way the coil is distributed spatially, the way the receivers are distributed spatially, with the way we acquire the K-space, we can actually sample at sub-Nyquist levels. So we acquire aliased images, and then we use the coil sensitivity patterns to unfold the aliasing and accelerate the images. So this means we can now acquire images with multiple receivers much quicker. We use less RF pulses, and that means we can actually increase the flip angle and get higher signal to noise as well. So image acceleration with reduced RF encoding using parallel receivers here, that's acceleration factor 2, acceleration factor 4 without loss of image quality. So tricks to be played really with the technology to get images faster. Equally, we've looked at methodologies which involve compressed sensing. So here we're randomly sampling the K-space in an undersampled fashion, very much similar to the way a JPEG image is compressed. And these techniques don't require multiple receivers. You can do them with a single coil, and we get good 3D image acceleration with compressed sensing techniques. So the drive here being to increase the temporal resolution, and improve the spatial resolution. Moving along, now we've developed xenon imaging, we're very keen to see how it performs against helium-3. So there's a big body of evidence out there clinically about what helium-3 can show us. So the motivation for this work was to see if we can actually acquire the two gases at the same time. So here we've built resonators to pick up proton signal, helium signal, and xenon signal at the same time in the same breath. So we've got triple nuclear imaging of the two gases and the structural imaging from the proton MRI at the same time in the lungs. And bringing together the structure and the function tells us a lot about the lungs. So structural changes with function from the two gases. For example, helium-xenon got very different diffusion kind of coefficients in terms of their Brownian diffusion, so they probe different length scales within the lungs. So if we can bring the two gases together at the same time, we can learn more about lung physiology from that. Some volumetric examples there. So quick comparisons really. So helium and xenon, comparable image quality now. We see that helium in partially obstructed lungs tends to get into spaces more easily than xenon does, and you'd expect that because it's more diffusive. It's able to kind of penetrate partially obstructed airways. But if we summate the ventilated volume as of the lungs with the two gases, we see good correlation in patients. This is some work from Cincinnati. So this is Jason Wood's group over in Cincinnati, and they're now using xenon MRI in pediatric patients with cystic fibrosis. So these are kids who are born with a genetic disease. Their lungs fill with mucus over time. The lungs become more and more obstructed. With the right treatments, these children will now live into and beyond middle age. And using novel imaging to actually help these children with their treatment is very important. We don't want to be giving them CT to avoid the ionizing radiation. So these are some equivalent images in Sheffield we've got. So here's the CT scans. 3 examples with normal CT. So no structural abnormality in the lungs of these children. But with the inhaled gas MRI, you can clearly see the early obstructed airways related to mucus plugging of the lungs. So using these techniques now in the clinic as an alternative to the ionizing CT is very much of interest. We're also using the techniques to evaluate lung therapies. So here we've got an asthmatic patient who's abstained from taking their bronchodilator. Then they've taken their bronchodilator and a large part of the lungs has responded favorably to the drug. Using a kind of paradigm of treatment response mapping, we can come up with a response map of the lungs, and you can see in this patient, parts of the lungs that have responded have generally responded favorably. So that color map represents lung ventilation increase quantitatively. So more sensitive ways of picking up change of the lung to a therapy, and also which bits of the lung are responding to the therapy using these techniques. And the nice thing is we can repeat them over and over again. They don't use radiation. So the drug companies are now quite interested in these methodologies as sensitive kind of outcome measures for their new drugs. If we go back to the diffusive properties of the gases, I said helium and xenon have got different diffusion coefficients. We can, however, tune the way we measure the diffusion such that we sample similar kind of length scales with a given diffusion time of our magnetic resonance sequence. So we measure diffusion with MR using a Stage-Gold-Tanner type technique using pulse gradients, and atoms that are moving faster and are less impeded, their signal is attenuated more. So in a healthy lung, we have a low diffusion coefficient. And in a patient with emphysema, where the alveoli are destroyed and the mean free path of the gas is larger because it's less impeded, we see elevated diffusion. So with helium and xenon, we can measure the diffusion coefficients in patients and normals, and we see that definitely they both pick up the same kind of pathology in the lungs. And preliminary data shows that the two correlate. Now, the diffusion coefficient itself is not a direct measurement of length scale. It's proportional to it in some way or form, but in order to get quantitative information about lung structure, we need to somehow get an estimate of the mean free path of diffusion. Unfortunately, gas diffusion in the lungs, when we measure it with NMR, is not Gaussian. we get a deviation from an exponential behavior as we successively applied diffusion gradients of increasing strength. And this is because of the diffusion regime these gases are in the lungs. However, we can use that deviation from the Gaussian diffusion approximation to actually come up with models of lung microstructure from the diffusion behavior. So by acquiring multiple gradient sensitizations, we can come up with parametric maps of mean linear intercept using a variety of models. So this one's based on a stretched exponential model, which transforms the signal back to a Gaussian phase approximation. And from this, we derive maps of the mean linear intercept. So this is what a pathologist would do if they were looking at a microscope slide of the lungs. They would call the mean linear intercept would be how frequently they crossed an alveolar capillary barrier when looking at the lung histology. So these are now quantitative maps of mean linear intercept in the lungs in micrometers. And we're now acquiring these in 3D. So in order to validate these diffusion-weighted techniques, we've been doing some work based on micro-CT. So here we've taken micro-CT from pathology and segmented out the acinus. So that's the alveolar acinus. And now if we solve the Bloch-Torrey equation inside that geometry, we can predict the diffusion in the acinus, and then we can relate back what that measured diffusivity is like when compared to the measurements we actually make in vivo. So although the pixels in our measurements here are quite large, they're about 5 millimeter cubed, we are getting quantitative information which is microscopic. So basically we're subvoxel information on lung structure, and we're validating that with computational simulations of the diffusion behavior. So moving back to xenon and its interesting properties, as I said earlier, it's soluble. So here we've got the gas phase signal of xenon in the alveolar space. So that's xenon atoms bouncing around in the gas phase, but it's soluble. So it will get, by diffusion across this wall, this alveolar capillary wall, it gets into the bloodstream. It's a small signal. The Ostwald dilution coefficient of xenon in blood is not high, but it's measurable. And equally, we can actually measure the signal from this barrier. So here, if we've got tissue, basically skin, in the lungs, we can measure the signal from the barrier. So in interstitial lung diseases, where we've got alveolar capillary thickening, this is a very interesting technique because we can potentially measure the barrier thickness in fibrosis, lung fibrosis. I might point out that these two signals have got a very short T2 star. So the gas, we have motional narrowing, so it's got a nice narrow line width. The dissolved phase signals, because we have a process of chemical exchange processes taking place, you get exchange between these two peaks, and we get a broadening of the peaks. So as well as being small, because the gas is not very soluble, they're also short in terms of the relaxation time. So imaging these two is challenging, but it's possible. If we stay with spectroscopy, though, and if we look at the uptake of signal from the gas phase into the blood and measure it with time, we see some very interesting effects. So here's a histology slide, micro-CT of a normal lung, and that's histology of a fibrosed lung, someone with interstitial pulmonary fibrosis. You can see lots of kind of tissue in the lung walls, in the tissue microstructure. So here, if we look at the uptake of the signal in the tissue plasma and the red blood cells, you can see that the diffusive uptake in normal lungs is a lot quicker than it is in patients with lung fibrosis. So much slower uptake in the blood cells and in the tissue. And that's reflected in the spectra as well. So in a healthy lung, you can actually see the red blood cell peak. But in a pulmonary fibrosis lung, it's dominated by this tissue peak. And that's because their lungs are fibrosed. What we can do now, though, is solve the diffusion equation for gas transfer across this membrane. And from this, we can come up with estimates of the septal thickness. So this is solving the 1D diffusion equation across the wall. And if the wall is thicker because the lung is fibrosed, we can measure that. So from solution of the 1D diffusion equation, we come up with an estimate of the septal thickness of the barrier. And we see that this is a very sensitive marker of alveolar thickening. So here is pulmonary fibrosis patients. They've got a much greater average septal thickness than healthy volunteers. And these are patients with rheumatoid disease of the lungs, so it's called systemic sclerosis, but they also get a thickening of the membranes in the whole of the body, fingers, toes, everything, but also in the lung tissue as well. So we're able to pull out significant differences there. This is the lung function test, which is closest to a xenon kind of diffusion transfer. It's the diffusion capacity of carbon monoxide. This is a test that's made in the lung physiology lab routinely. And our NMR parameter of septal thickness correlates very well in an inverse fashion with the carbon monoxide transfer factor. So going back to our simulations of diffusion, we've now applied a similar kind of technique here. We're no longer solving the Bloch-Torrey equation for phase. We're just looking at mass transfer, and we're looking at how xenon seeps into the fibrosed portions of the lung where you've got interstitial thickening with time in order to corroborate the measurements that we make in vivo. So this is some work that Neil's recently published in JMAG-Res. And you can see there where you've got fibrosed tissue, much longer uptake times of the xenon magnetization, longitudinal magnetization. And then that allows us to then go back to our measurements that we make in vivo and kind of make sense of what it is we're actually measuring. So that's dissolved xenon spectroscopy in the lungs. With optimizing the sequences, we can actually image it now. So here we've got a xenon ventilation and perfusion scan in the same breath. And because the gas peak and the dissolved peak are so far apart in ppm, they're 200 parts per million apart in terms of chemical shift. If we apply our frequency encoded gradient in that direction, in the same scan we get a gas image and a dissolved image. So this is basically a chemical shift artifact due to one of the resonances being off resonance, but we can actually get 2 for 1 in the same scan. So we've done lots of work in trying to selectively excite the dissolved signal so as not to batter down the gas signal, which is our reservoir of polarization. So dissolved phase imaging of xenon, you really want very, very selective RF pulse excitation on the dissolved signal in order to not kill the gas signal, which serves as a reservoir of magnetization. So yeah, similar kind of methods in 3 dimensions now. Low signal to noise, but we hope we can improve this in years to come with improvements in gas polarization and the pulse sequences. But 3D kind of ventilation and perfusion scans with xenon MRI. Coming back to the xenon chemical shift, xenon's sensitive to the paramagnetic conformational state of hemoglobin in blood. So hemoglobin's paramagnetic. If you go back to the papers of Linus Pauling, they did a lot of interesting work on the paramagnetic effects of hemoglobin. And now we've been looking at this in vivo with the xenon chemical shift. And we see as we deoxygenate blood, this is the Farhouse curve of blood partial oxygen pressure. We see that the xenon chemical shift comes closer together. So the gap between the tissue plasma peak in the lungs and the red blood cell peak comes closer together as we hold our breath. As oxygen partial pressure goes down, the 2 chemical shifts get closer together. You can also see the cardiac pulsation of the xenon signal in the lungs as well, due to the pulmonary blood pool as the heart pumps. You see with time, the red blood cell peak is pulsating. But what's interesting from this, we can actually map the blood oxygen partial pressure, so the oxygenation of the hemoglobin molecule in the lung with apnea as you hold your breath. We see that the blood oxygenation goes down here. So we're now trying to evaluate this method in patients who've got impaired gas transfer, people like fibrosis patients where oxygen uptake across that impaired barrier of the lungs is impaired. We've also done some work looking at the relaxation time of xenon. And again, that's oxygen dependent. This is work done by Graham. We see that the relaxation time of the red blood cell and plasma peak of xenon in the lungs map each other very well because of their in constant chemical exchange. But it's oxygenation dependent. So in oxygenated blood, we've got T1s of about 8 seconds. So that means that inhaled xenon can get beyond the lungs. So we're now picking it up in the brain and other organs which are perfused with xenon in the blood. So some early work here that we did in humans. So here we're measuring with spectroscopic imaging this time, different peaks from the xenon in different compartments of the brain. So here you've got xenon in the grey matter in the brain. Here there's a xenon in the white matter. We actually see xenon down here in the face as well and in the tongue. And if you breathe xenon in, you know what I mean. You get a tingling in the tongue, and that's because the xenon is dissolved in the blood in the tissue there. So we're now picking it up in the brain, and we can monitor the uptake of xenon in the brain and how it goes from the gas phase into the blood phase and into the different tissue compartments. It tells us something about the transfer of xenon across the blood-brain barrier. So typically when clinicians image brain perfusion, they use gadolinium contrast agents. It's a chelated gadolinium contrast agent, an injection in the arm, and the blood carries the contrast agent to the brain. Now, these contrast agents are not permeable to the blood-brain barrier. They're in an intact blood-brain barrier, they stay in the blood. Xenon crosses the blood-brain barrier, so it makes it a very interesting potential contrast agent for looking at abnormalities of the blood-brain barrier that take place in a variety of neuro diseases. So we've been very interested in now trying to image xenon in the brain. So here's some preliminary results at 1.5 Tesla and at 3 Tesla that we've got this last year. So that's dissolved xenon through a sagittal slice of the brain. And there you see that's a conventional proton MRI, which we've segmented for the grey matter signal, and you can see very good correspondence between the two. With improved coil designs now, so Madwesha's been working on, where is he? Yeah, there he is. So he's been working on optimizing these RF coils for picking up xenon in the brain. And now we're able to pick up the washing of the xenon with time and the washout of xenon with time in the brain using receiver array coil technology like this. And if we average these images together, we're now getting image quality like this. So potentially viable, I think, as a non-invasive means of looking at brain perfusion in years to come in a clinical setting. And we're very keen to evaluate this clinically now in brain diseases as well. So I'll just summarize. Looking ahead clinically, this is the kind of image quality we can now get with inhaled natural abundance xenon. I think with our new polarizer, with 500 ml doses of inhaled xenon, we can halve that, and it makes it potentially economically viable. Multiple sites are now evaluating the methodology around the world. So about 12 sites in the States, and I think there's now 6 sites in Europe and a couple in Japan are evaluating the techniques clinically. At the end of last year, we kind of did a world first, really. So we took this from a kind of research technique into clinical practice. So the MHRA is our regulatory body in the UK. This is the agency which judges what you can and can't do to patients, what you can administer and what you can't. And after a long journey with helium and then xenon, we've now got a manufacturer's specials license. So this now means that a clinician can request a hyperpolarized gas lung scan for clinical reasons. So we're now doing clinical referrals with these techniques in the clinic rather than just doing research. And this is our first patient that was scanned. So this was a patient from the Children's Hospital. She had non-cystic fibrosis bronchiectasis. She was an elite athlete. She is an elite athlete. She's a 13-year-old runner. She looks very healthy. She knew that her lung function was going down. Her exercise capacity was going down. When she went to the clinic, her lung function tests were all normal still. Her spirometry was all normal. Spirometry is a very insensitive test. It doesn't pick up early-stage lung disease, early-stage lung obstruction. When we did the first scan on her at baseline, we saw significant abnormality in her ventilation scans. So relatively normal lung function, but impaired lung ventilation from the imaging. So added clinical information from the imaging. So her clinician, her doctor, then put her on intravenous antibiotics. And general picture is most of the lungs responded favorably to the treatment that he gave her. And you can see that in the imaging. And then he put her on a different treatment and things got worse again, and we saw that as well. So lung ventilation volumes are comparable, but the spirometry is now going down. So with this kind of methodology, we're now able to follow up patients. This is a child. You wouldn't want to give them a CT scan. You wouldn't use ionizing radiation. We now have a very sensitive technique to follow their, diagnose their lung disease and follow it up with time and how it responds to treatment. So just to summarize, really, I would say that we can now place our technology in this kind of space, really. We've got more sensitive methods to pick up physiological abnormality, early detection and diagnosis, helping the clinician manage the treatments and also assess the treatments. Excuse me for the joke. I'm from Sheffield. We make knives, so we've got sharp tools for imaging lung disease, which are underpinned by techniques which were pioneered here in Paris. And I think I feel quite kind of happy to bring this information to this audience, because I think after a long time we're getting somewhere clinically with these techniques, and I hope within my working lifetime they become distributed everywhere. I think it's feasible, I think it's achievable from a technology point of view, and I also think it's cost effective if we can help clinicians put certain patients down certain pathways that save them nasty interventions. So I hope in 10 years' time we've got a much bigger body of evidence from around the world to show that these techniques are useful. Lots of people have worked with us over the years on the technology side, also our clinical collaborators and our collaborators from different parts of the world. These guys are the kind of core xenon team, I would say. Big optical pumping cells here, very important, large glass cells. Yeah. Okay, thank you.
So thank you very much for this very interesting talk and for discussing the connection between basic research and clinical applications. And I have a question about that. It's, I guess you have to train medical doctors too. It's not only a question of money. Or are the pneumologists getting into this field? And what can you say about that?
Yes, good question. Typically, imaging in a hospital is managed by a radiologist.
Yes.
But the logical home for this technology is with a pneumonologist. So we're getting more traction actually from the respiratory physician than from the radiologist. So we've spent a lot of time actually going to respiratory meetings and talking to the clinicians for this reason. And they like it, but they ask us, can we compress all of our regional information we get from images into one number that allows them to make a quick diagnosis. So I think part of our battle is to actually convince them that they have to look at images rather than, you know, one number. Yeah.
Thank you. Yeah, two remarks and one question. The first remark is that I congratulate you to this fantastic xenon polarizer which you made, and which makes the signal almost equivalent to the one which you get with helium-3. This is of utmost importance, of course, because helium-3 you will never have for clinical use any longer, since the price has risen by a factor of, what is it, 50 or something like that. Yeah. And but it is not polarized xenon. It's not only important in your business, but also in fundamental physics for looking after basic symmetries like time reversal and electric dipole moment of the and so on. So maybe we should ask you about your polarizer at some time, yeah? So it comes back to fundamental physics, yeah? Yeah,
well, we learned from you in the first place, so I'll be very happy to talk to you about that,
yeah,
yes.
And the second remark is the following, that when we started with helium-3, But we couldn't do this alone. So Werner Heil and myself, we spent a sabbatical here at the ENS almost 30 years back, and got the help by Michel Leduc, by Jean-Pierre Pierre-Jean Naché, our organizer. Thanks you, Pierre-Jean. And yeah, okay, yeah. And Geneviève Tastevin, yeah. And I wanted to mention this, that without their help, and they also published with us some papers. No? And now the question. Helium-3, with helium-3 you were able to measure the uptake of oxygen in the lungs, because the relaxation rate of helium is proportional to the pressure of the partial pressure of oxygen. And how is it? Has this also died? I didn't follow the recent.
Yeah, no, it's not died. We find it to be a very useful technique. We have to be careful in patients where the diffusion is so enhanced, where emphysema has destroyed the lungs so much, that you have to be careful that the gas is not diffused from the point in space where you're measuring the relaxation time within the time course of the experiment. So it takes 10 seconds to measure the T1. If the gas has diffused a distance in that time, then you can't really compute a reliable map of relaxation because the gas has moved around. But in patients where the lung microstructure is not totally emphysematous, it's still a very useful technique. We can also do the same with xenon, but the dipolar interaction is not as strong, so helium is much better for mapping the T1. Yeah, but yeah, I'd say it's still a. I'm sorry I didn't give not time to show everything. It's yeah.
Bill, your turn.
So first, I want to say just how amazing it is that you can polarize this xenon in with optical pumping and spin exchange, and then freeze it in a magnetic field, and then use it a long time later. I just find that so remarkable that that the spin polarization is so robust. The mixture, the gas mixture that you use to do that process has 10% nitrogen. Now, I mean, normally you would think nitrogen's a bad thing. So what's the nitrogen doing for you?
Well, I think it's preventing collisional mixing. I think that's kind of my understanding is we need it for that. But also, we're in a regime where van der Waals intermediate molecules are vital for spin exchange, if you know what I mean. So the nitrogen becomes a kind of buffer. It's not just a buffer gas. It's implicated in the spin exchange process.
I see. Okay.
Yeah.
Now, if I understood correctly, you said that a standard clinical test has to do with diffusion of CO?
It does for measurement of alveolar capillary diffusion, yeah.
I mean, doesn't that strike you as being kind of funny to have people breathe CO?
You're talking about very small quantities, yeah. But it's, I believe someone has now polarized CO using DMP as well, I think, or maybe parahydrogen. But you might well see people making NMR measurements with CO in the future.
Okay.
Yeah.
Wow.
Michel?
Okay, thank you. A comment on Bill's comment and a question, a medical question to you, Jim. I am very happy that the work that was started with this European field program could be continued with xenon when helium become unavailable. But about the relaxation, I would like to mention that before the first experiment was made on a human being together with Erstotten and others with the helium-3 in Heidelberg, nobody had any idea what would be the relaxation time of the helium-3 in the lungs. And calculation had, predicted it would be very, very short. And the first measurement, it was a big surprise to find 4 seconds, which was long enough to make a measurement. And after that, it was also easy to calculate a posteriori, but it was not obvious. I have a question for you. At the time of the field European project, a comparison was made with xenon, and xenon was supposed to be not harmless. Helium is harmless when you swallow, but you inhale. But xenon is supposed to make you dizzy and a phantasm to dream about strange things, and it was supposed not to be adequate for trial population of weak people. They could be, annihilated because it goes to the brain, as you nicely mentioned. And,
I guess it was only for xenophobic people.
So is it not something that could prevent it to be used at a large scale in hospitals?
It's a good point, and if you breathe xenon in very large doses, more than 1 litre, you will feel, if I hold my breath for 20 seconds with a litre of xenon, afterwards it feels like I've had a couple of whiskies too quickly, but it's quite a pleasant feeling. But I can, you wouldn't want to ask a patient to do that, and that's why we've made big efforts to reduce the dose. So with a 500 milliliter dose and a short breath hold, you don't actually feel the effect. So now we've done studies in children with small doses, and they don't feel the effect. So it's something we have to be aware of, but it's something that we can deal with increased polarization.
Okay, so thank you very much for this talk.